Good morning, Jesus.
Good morning, Professor Garret. How are you?
Pretty good. I've been trying to sign in with my regular computer, but they want me to update. And then I'd have trouble updating, but I'm using my laptop. It seems to be working all right. I hope somehow it doesn't require an update, even though I haven't used a laptop or Zoom in a long, it's just, this technology is pretty funny.
No. But now you have no problems with your computer.
Well, I'm using my old laptop, but it seems to be working just fine. So I'll just use that. But my desktop was Ubuntu, and somehow they don't handle Ubuntu so well as this is Windows 7 that I'm using, and it's working fine with no required updates or anything.
Okay.
I see Bill is in there now. Good morning, Bill. Maybe Brian is there too, I think.
Good morning to all. Good morning.
Good morning, Ryan.
Yes, Dr. Sobczyk, you, good morning, Brian. Dr. Sobczyk, you mentioned there were two other people who might be attending today.
Yes, did you send them invitations, links?
Yes, I did send something, only recently though, about 15 minutes ago.
It's difficult to say. A couple of them, one was a former student at FESC, Juan Manuel Torres. He was there many years ago when I was there, and we happened to meet up. He was interested in joining, but I only got to send the message just yesterday, so people are busy. There's no doubt about that. But at least they have my paper. I did send them a copy of what I would like to talk about today.
Okay.
And the other people were two engineers from Volkswagen, which are in Puebla, which are very interested in geometric algebra and had worked with me on a chapter that was in my Matrix Gateway book.
Okay, well, I hope they are available. If not this week, then maybe in 3 weeks' time. Okay, I did receive your email. However, I really have to admit I haven't had a chance to look at your most recent draft. I presume it's a draft, son?
Yeah, it's material. I haven't decided I haven't posted it anywhere except sending it to you and the other possible participants of the, I sent a copy to Brian as well. So.
Okay.
So I can, if we're ready to start, I can try open. I haven't used my laptop for a while, but I do have. I can try sharing and see if I can pull it up on the screen. Then we get started.
Sure. I think that's fine. Jesus, did you have any other comments, or did you have any plans on things we should do in the future? Jesus, are you there?
Yes, sorry.
I was just giving you an opportunity to say whether you had more things you wanted to talk about in terms of category theory, or whether we might do that in 3 weeks' time, something like that.
Yes, I continues working with this same idea of relate Clifford algebras and graph theory. I found in some papers related with that, And in fact, I found in one reference that I have used before some ideas about the graph and Clifford semigroups. Then I think that I don't not sure that this is in the way that Professor Garret first proposed about a relation between a complete graph and Clifford algebra. But I think that it could be interesting to review those ideas, and when I am working in this way, I found much information, but at the same time it is more complex. Then I need to review more about the ring theory, for example, and review more about the category theory and graph theory. Then it is a complex problem, but I think it is too much interest. Then maybe only in the idea of present, how I am working with this, I can prepare something for this next session.
Sure. I think it might be interesting even if you could just sort of outline some of the references or some of the papers that you're looking at, in case we had an opportunity to sort of do some background research ourselves, I guess.
Yeah, my only question was, did you have a chance to look at this Dr. Tanya Kovanova's paper? She tries quite a bit with Clifford algebra and graph theory, which I found interesting. But again, there's a lot of material there.
Yes, I saw the Kovanova paper, but I think that Kovanova is taking another way for working with graphs, because there we have a simple graph in a line, and there are expressed some ideas about the Clifford algebras. But in the idea of working with a complete graph, I think that we can avoid this like a complete system, a closed system, and then I think that it could be more interesting. I don't read careful the Kovanova paper, but I only make a general view of them.
Well, yeah, I can't say I've done much more than that either, but yeah, I noticed that she was much more dependent on, she was mixing Clifford algebra with matrices and going back one to the other without making much distinction, which, well, is interesting, and also might give ideas to how I could even continue what I'm trying to do as well. But it's, I think the graph connection is very interesting in regard to the work I'm doing right now with these width bases, specialized width bases, which is what I want to talk about today, actually. The difference between the two types of bases, which is a problem that you brought up last time, or a couple of times. What's the relationship between standard duality and what I'm calling now quantum duality? And it really just is, well, that's what I'd like to talk about today, actually.
Sure.
Okay. Okay.
I just have a comment on that, Professor Garret. When I read the paper you sent us, I think the idea is really close to strong correlated bases that some Oxford group use in CX calculus. So it could be interesting if you can check that area too to complement this idea of the width basis. I think it's really close.
Yeah, if you had any
But
particular references, you could send them to me by email.
okay,
That would be very
okay.
helpful to find the Oxford group that you're talking about. I don't know about them. I know about the Cambridge group, but I don't really know about the Oxford
This
group.
group is only working on a kind of a category theory derived calculus to deal with quantum computing, but they find some rules that are really interesting. Some of them treat with a strong complementarity, which are like, I think they are related with the idea of the width basis, because it's not like a normal orthonormal basis. It's more it has more information between them, so it's a special. But I will
Yeah,
send you the
that is
paper so
interesting
you can
because
check it.
that's right. That's what people, you normally with a width basis, it's an orthonormal basis, but the basis I'm talking about is not orthonormal. In fact, the inner product of any two null vectors is 1/2, which is the interesting point.
Okay, okay.
Okay. Um, well, if you're ready, Dr. Sobczyk, you could perhaps share your screen in the usual way. And
Okay, let's see if I can do that. Yeah, maybe I should open the document here first. And then I should appear then when I share screen then. Let's see here. Okay. How does that look? Can everyone see that? Global and local nilpotent bases of matrices, is that on your screen?
Yes, we can.
yes, I see it.
Okay, so
problems?
maybe I can start then. So I begin by the usual thing I've been talking about. But now I'm making a distinction. I say, first of all, I define what I mean by globally correlated dual geometric algebras, which is that's the usual standard width bases that are orthonormal. And that's between two geometric algebras. Okay, so we can go over. So here I just give that definition of the standard, what I call a spectral basis, where the idea of a spectral basis arises, is really with the standard notion of duality between two vector spaces. And in this case, we're taking dual geometric algebras to represent dual Grossman algebras to represent that duality. Okay, so that's what I'm defining here. I first define what we mean. A nilpotent, okay, is any quantity, algebraic quantity, which has square equal to 0. And two nilpotents are said to be anti-commutative if they satisfy this relationship number 1 that you see. And then I define a Grossman algebra, namely take n null vectors, which are linearly independent. Well, since we're saying that they satisfy this relationship 1, they're all anti-commutative, which is, of course, what defines the basis of a Grossman algebra. And so the one Grossman algebra, which I'm denoting by G of this set of n nilpotents, denoting that by G of AN. And I'm taking it over the field, which in my case is either the complex numbers or the real numbers. mostly I'll be talking about the real numbers, but the complex numbers becomes very important as far as interpretation in quantum mechanics and so on. So I want to leave open that possibility. Okay, so it's just F then is a scalar field which commutes with all the elements, all the null vectors in the algebra. It's just, okay, so now I'm saying let Bn be a second set of n nilpotents, which I call B1 up to Bn, and then also they're anti-commutative, satisfying this relationship number 1. And again, so now we have 2 Grossman algebras, which I'm denoting by G of An and G of Bn. Okay, and now I have this property number 2, which is really the dual relationship. I'm correlating what I'm calling globally correlating these dual Grossman algebras if they satisfy ABJ, AIBJ times BJ AI is equal to the standard delta function. So that means, of course, if I is equal to J, it's equal to 0. Now, if I is equal to J is equal to 1 and I not equal to J, the delta function is 0. And this is for all IJ. So this is then what I call a globally correlated or dual, representing dual null vectors. I might mention that Zbyszko-Ziewicz talked about this quite a number of years ago in looking at this duality and making the dual vector space a geometric algebra as well as the vector space itself. So that, of course, all these ideas are closely related. Okay, but I'm actually now, I'm saying globally correlated Grossman algebras are an equivalent way of representing dual vector spaces. So that's the main point I'm making here.
Now, can I ask you a question when you talk about dual vector spaces here? I mean, how do you define the notion of dual in this case?
Well, for example, if we look at this relationship 2, usually we say that instead of using a dot product, we're looking at these I'm looking at these nilpotents AI and BJ as being in the same vector space. So it's really a set of n vectors related to a second set of n vectors, but really that's really equivalent to the notion of duality. It's just another way of looking at it. You can think about this as being an operator. Instead of being an inner product between 2 null vectors, the AI are null vectors and the BJ are the dual vectors. So you can think about being an operator BJ of AI is equal to delta IJ, rather than interpreting them as 2 null vectors. In the same space, you're in the usual way of a duality is the BJ is an operator on the AI to get the delta function then. Is that clear what the relationship is between? It's just another way of representing duality, the standard duality between operators and vectors. Well, usually it's defined as an operator. BJ is an operator on the null vectors AI equal to the delta function delta IJ. I suppose it's it's a small distinction, but so I'm saying that these Grossman algebras are dual to each other if they satisfy this property number 2. That's all I'm saying now.
Yeah, well, certainly that definition is clear. I'm just the statement, the last sentence, in fact, I guess is sort of.
I believe it's just
it makes
another
it seem to
equivalent
me
way
as
of
if
representing dual vector spaces. In fact,
but your statement makes it seem obvious, and maybe maybe it wasn't immediately obvious to me what you meant here. So I'm just
notice that I am defining this inner product.
Yes,
but
yeah,
you could just cross that out of there and just say, but that's the interesting thing. That now I'm really interpreting globally correlated null vectors as a Clifford algebra. When I define this inner product between these dual bases as being elements of a Clifford algebra, both of them, AI and BJ, are elements of the same Clifford algebra. And that's going to be the algebra we identify with G, the Clifford algebra of neutral signature, GNN.
Mhm.
Well, maybe I'll go on to the next page.
I was just thinking that that last sentence potentially requires a proof. You know,
Oh,
that's
well. Okay, well, I want to put it all in the Clifford algebra so you can see how it works.
Okay.
And okay, so that's theorem one. So that would be where a proof would be maybe desired. Okay, theorem one, let's see what it says at least. A pair of globally correlated Grossman algebras, GNA, that's a Grossman algebra, and GNB form a width basis and generate this, what I call the spectral basis of the geometric algebra GNN, isomorphic to the 2 to the n cross 2 to the n square matrix algebras, matrix 2 to the 2n of F. Okay, it's 2 to the, matrix, it's 2 to the n cross 2 to the n square matrices then in this particular representation. And now I'm writing it because geometric algebra is compatible with matrix algebra, obeying exactly the same rules of matrix algebra. I don't have to go through all those rules, because when I set my define my null vector space, I said that they obey the same rules as matrix algebra. So I can use matrices with the elements of these matrices are actually geometric null vectors. So I'm writing now as a column vector. You can think about this as being a proof. Okay, the proof that you were looking for in the simplest case of G11. Okay, so let's construct the basis then for the familiar 2 cross 2 real matrix algebra, which is the matrix algebra 2 by 2 matrices over the real numbers. Okay, so what I do is I put 1 and then the first null vector A. There's only, okay, and then I write BA here, and BA is actually a well, it's a nilpotent, it's an idempotent. Okay, it's a okay. Well, we can prove that by that multiplication table that we give, BA times BA is equal to BA. And that's because of this correlation that we looked at. That's because of this definition here is equal to delta IJ. It will follow from that. But okay, let's go on to that. Okay, so this then generates the basis then of the matrix algebra. I call BA, BA, and AB. Okay, so these are idempotents. So BA times BA is equal to 1. AB times AB is equal to 1. And now you can see I can write the matrix of that geometric algebra now by simply turning this definition around slightly. Well, writing it in this way, because that's an idempotent, I can multiply BA times 1 is BA. BA times A is equal to A. Okay, that's that rule that we talked about before. And anyway, so, well, here it is then. So the matrix of the null vector A becomes 0, 1, 1, 0. Well, 0, 0, 1, 0. Matrix of the element B consists of 0, 0, 1, 0. Matrix of the idempotent BA is 1, 0, 0, and AB is in this way. So, okay, and now I'm going to define what's usually identified as a standard basis of the geometric algebra of signature quadratic form 1, 1. Okay, we define the vector E as a sum A plus B, F is equal to A minus B, and then we calculate E squared equal to 1 is equal to minus F squared. Well, that's the usual basis of the geometric algebra G11. Notice now that the bivector E times F, well, that's just the product of A plus B times A minus B. Okay, and I want to give you that usual table I write down on page 4. I'm not going to repeat it because I'm really trying to say that this one multiplication table on page 4 is all we need. Well, I can skip over to that, I guess, quickly to so you can refresh your memory. There it is. So that's the multiplication table I've written on numerous occasions. So you have the nilpotents. A squared is equal to 0. AB is AB. And we have ABA is equal to A. And BAB, let's see, B, okay, B, yeah, B, let's see here. Oh yeah, B squared is equal to 0. B times AB is equal to B, and then B times B squared A. Well, that's B squared A is 0 again, and so on. So that's the usual table that I've written down on many different occasions here. Anyway, this is the simplest way of seeing what we mean by the spectral basis of the geometry. Okay, so you have the geometric algebra of neutral signature, or some people call it the mother geometric algebra. It's generated by two null vectors, A and B. And their product now is this idempotent. It's a, what's the name of that idempotent? If it's, I forget that's a special kind of, oh, it's, well, the name will come down to me. I'll recall it in a minute, but it's simply it's an idempotent that has cannot be further simplified. It's a, what do they call that, the idempotent?
Atomic?
Pardon?
Atomic?
Not atomic, non-decomposable idempotent. I guess that's what, but there's a
sounds good.
special word for that that I'm not remembering. But anyway, but now if we look at the basis for the standard basis, the interesting thing is you get the Pauli algebra. Okay, you get E1 is just A plus B. Okay, so the matrices of A and B add together to get this matrix. The matrix of E2 is, well, now you see, I need that I in there, okay? But the matrix for E3 is 1 and minus 1. Well, that's the same thing as BA minus AB. Okay, that's this null vector, the bivector E times F. Okay, so that's the interesting one. Of course, that's the Pauli matrix for the vector E2. But okay, now if I write that in terms well, now we're doing a few tricks here, because the geometric algebra G11 is generated by the vectors E and F. But you can think about that as being a subalgebra of the geometric algebra G3, where you're identifying vectors. The vectors in G3 now are the vector E1 with the bivector E1 times E3. Now that, of course, is strange, but notice that E1 will anti-commute with E1 times this bivector because they have one vector in common. So really to identify, well, we can say that the geometric algebra G11 is isomorphic to a subalgebra of G3 generated by the vector and the bivector E1 times E3. Okay, well, now I'm just writing down then how to write then the coordinate matrix of any geometric number in G3 then can be written in this form. Okay, so G is a coordinate matrix with respect to that, what I call the spectral basis. And that was our basis that we looked at. Oops, I don't want to do that. Yeah, okay, so again, we have BA, BA, and AB. That's the spectral basis. So those are idempotents and those are null vectors there. But notice that everything is generated by those null vectors. That's the, well, which come out of two Grossman algebras. Remember, when we generalize to n dimensions, we have A1 up to AN and B1 up to Bn, and they generate separately two Grossman algebras. That's why we say those algebras are dual in a certain sense, well, related to the usual concept of duality. And that's what I want to distinguish in this talk by this other concept of duality that we will talk about then. Let's see if I can get control of this. I think I'm all right. Okay, so all right here, I'm just proving that this bivector E times F is equal to 1. And that's what we call a hyperbolic bivector. Remember, a Euclidean bivector has square minus 1. Okay, but because one of the vectors which make up this bivector has signature -1, F squared is equal to -1. When we calculate U squared, that's a bivector which has square plus 1. So I'm calling that a hyperbolic bivector to distinguish it from a Euclidean bivector. All Euclidean bivectors have square -1. So again, you're able to, there's many square roots of -1 in geometric algebra, which is of course well known. But I think that's one of the reasons why matrix algebra has been developed on itself, because a very convenient way of multiplying matrices is the usual row times a column, or a column times a row, to define various elements in the matrix algebra without having to say what's a vector, what's a bivector. And of course, there are many different interpretations that you can give a matrix, depending upon what you are doing. But that's where I find, okay, so I'll mention that again a little bit. So, okay, so unit hyperbolic vector. So unlike a simple unit Euclidean bivector, which has square -1, okay. Okay, so that's, I'm just writing U plus a new notation, defining as 1/2 times E times F. Well, 1/2, and that's an idempotent. Okay, it's very easy to show that that's an idempotent. In fact, it's a principal idempotent. Maybe that's the word I'm looking for. Principal irreducible idempotent. Okay, because it cannot be written as a sum of two other idempotents. Okay, so that's an irreducible.
Primitive idempotent.
Pardon?
Primitive?
Okay, yeah, a primitive idempotent. I think that's another word. And those are very important in any matrix standard matrix representations depends upon identifying the primitive idempotent in that algebra, and which is what I do for this standard, what are called mother algebras, signature G1, GNN, or GNN plus 1. Now, if you add another vector which has square -1, then that's the same thing as complexifying the algebra, the Clifford algebra then, which is very interesting. Okay, anyway, so, okay, let's go on then to the next page here, which I was already at. Okay. Okay, so let's see then. We have seen in definition 2 that two sets of linearly independent nilpotents. Well, in the simplest case, well, A1 to AN and B1 to BN, where I'm defining this globally correlated or dual relationship between these two Grossman algebras, is defined by this relationship 7, which I already gave you. Okay, we've already discussed the case when n is equal to 1. The next case is when n is equal to 2, identifies real and complex 4x4 matrices as coordinate matrices of the real geometric algebras G22 and G23. For G22, we define U1, these primitive idempotents. U1 is equal to B1 times A1. U2 is equal to B2 times A2. And now the product of those, U1 times U2, is a primitive idempotent for the geometric, well, actually, you can see where it occurs. It occurs in the space 1, 0, 0, 0, 0, all the way out the line then. So that's the primitive idempotent for the matrix algebra corresponding to the geometric algebra G22. Now, G23 is where we're taking, if you look at the pseudoscalar of G23, you'll find that's in the center of the algebra. So it behaves like complexifying. So you consider G22 over the complex numbers is isomorphic to the geometric algebra, the real geometric algebra G23. So again, this becomes it because these algebras G22 and G23 are closely related to the Dirac algebra, Pauli algebra. This is why they're extremely important in physics. In fact, much of physics is done using the Dirac algebra and the Pauli algebra, which I have studied in many of my different papers, which I give as references to this paper as well as my other papers. Okay, so here's a spectral basis for two Grossman algebras, which are dual to each other, which I claim is well known as another way of representing standard duality relationships. And that's when when I identify what I'm calling quantum duality, you'll see the difference. It'll be very clear. There's only one Grossman algebra that's involved and not two, what I'm calling dual Clifford algebras in this case, which corresponds to the normal definition of dual vector spaces. One being an operator and the other being a vector space. So, of course, that was, well, you know, the history of mathematics, that was done during Cayley. Matrices were invented by Cayley and in the middle of the 19th century, and then I won't try to go through the history, but of course it's very interesting to see how the idea of duality arises, and of course it's one of the most important concepts of mathematics, a standard concept of duality, but it's not far-fetched to say that it's equivalent to this concept of two dual Grossman algebras as I'm defining it here. But we'll see how that corresponds then to the other idea then. Okay, so again, this is just a generalization of the simplest case, G11. We go to G22. And okay, the detailed structure of all real geometric algebras GPQ and complex geometric algebras Gn over C and their corresponding coordinate matrix algebras can be found. Okay, I give you these references. I try to help give you more details that you can look up. Most have references that you can find on the web. Given below is a multiplication table for the correlated nilpotents A and B. Okay, so that's where I define. So that's where I'm defining this multiplication table, which is I've given on many different occasions. So that's extremely important. But now let us look at this new way, okay? And now I'm going to talk about a different way of relating geometric algebras. But notice that by changing the signature of the geometric algebra GNN, you can essentially get all other geometric algebras by complexifying it. But that has a deep relationship to the structure of these so-called complex mother geometric algebras, which have signature n plus 1, n comma n plus 1. And that's where you can identify, instead of complexifying the geometric algebra GNN with the complex numbers, it's isomorphic to if you choose the pseudoscalar element of the geometric algebra Gn comma n plus 1, then the pseudoscalar element can play the role of instead of complexifying the real geometric algebra GNN, you can use the pseudoscalar element in the geometric algebra Gn plus 1. And that's important for interpreting geometric algebras. But what seems to be new, so basically the idea is you can, from the geometric algebras Gn comma n, you can get any other geometric algebra simply by complexifying it with I equal to square root of -1. Or you can recognize that the center of the geometric algebra Gn comma n plus 1, the pseudoscalar element, can be interpreted as the I equal to the square root of -1. Now you're free to do what you want in mathematics, and also, but in physics, of course, you're much more constrained by the physical model you're trying to build up of space and time, or space-time. And that's, of course, where a serious study of the Pauli algebra and its relationship to the Dirac algebra arises. I'll talk a little more about that in this section here. Okay, so let me talk about what I call a new possibility arises, okay? And now what we're going to do is we're going to choose, okay, I think it was always confusing because I started mixing the A's and the B's, but I don't really want two Grossman algebras now. I want to study one geometric algebra, one Grossman algebra generated by C1 up to Cn plus 1. Okay, okay, so now we're looking at a set of n plus 1. Why am I choosing n plus 1? Well, that's convenient to choose n plus 1, but it doesn't matter. But notice I'm only talking about one I'm picking a set of n plus 1 nilpotents, so they all have square 0, and I'm defining satisfy the following two conditions. Notice now I'm saying C1 wedge up to Cn plus 1 is not equal to 0. Well, in the standard way of looking at, with my Grossman algebra of the A, I took G, the Grossman algebra generated by the n nilpotents, A1 up to AN, or in this case would be A1 up to AN plus 1. And then because it was a Grossman algebra, I didn't need to put the wedge in there. But now I'm identifying the Grossman algebra as a wedge product between these vectors. So I'm just simply saying that a set of n plus 1 nilpotents with the wedge product defined as being the Grossman algebra, that it defines a Grossman algebra, which I'm defining as, under the wedge product, the Grossman algebra under the wedge product of these n plus 1 nilpotents generates 2 to the n plus 1 dimensional Grossman algebra over the real or complex numbers. But we can also define it over any finite field, for example, as long as characteristic is not equal to 2. Okay, in addition, now this is important, the null vectors in Gn plus 1 are said to be locally pairwise compatible or quantumly dual. This is a new concept, I believe. If for each distinct pair, Ci times Cj, Ci, Cj in the set of n plus 1 nilpotents, Ci times Cj plus Cj times Ci is equal to 1.
And
Okay.
sorry, Professor Garret, I have here some questions.
Okay.
Here, I understand you are building higher order algebra using the Grassmann product.
Yes, as a wedge, taking the wedge product now, so I'm leaving the inner product. I'm not saying anything about the inner product in my, in the top line here. I'm just saying the outer product generates a Grassmann algebra of dimension 2 to the n plus 1, the usual. But now you see, I don't want to say, here is here I'm defining what the inner product between those two, all those null vectors are. And in fact, it's saying it's equal to 1. But that's essentially the same thing as saying that, identifying that as Ci dot Cj is equal to, that's the, if you think about that, those elements Ci and Cj being in a Clifford algebra, they're in the Clifford algebra where the inner product of those two null vectors, 2 times the inner product is equal to exactly what that definition is. So the inner product then is equal to 1/2. Okay, so what I'm only talking about, and I claim that, okay, I'm going to show you why that's true. I'm not going to try to prove it right now, but I'm just making a definition which I claim is consistent, and you'll see why as I go along a little further. Okay, so but I'm trying to make a clear distinction of what I call the spectral basis, which corresponds to ordinary duality, and what I'm calling quantum duality is a different concept, and it relates the elements of one geometric algebra of null vectors, which I will identify in a minute. I'll identify what those Clifford algebras are generated by such n plus 1 null vectors. So I'm not using 2n null vectors in this case, satisfying the duality relationship, or what I call global duality. I'm using a local duality property right here. No, okay, notice, but what I write down underneath it is important. Notice that property 9 of local compatibility reduces to global compatibility when I is equal to j in 7. That is AB plus BA is equal to 1. And that's where this 9 is coming from. But now you see, I and j here are distinct. I is not equal to j. I'm taking each distinct pair. So that's a different concept than what I call my spectral basis. The spectral basis relates to compatible Grassmann algebras, where the Grassmann algebra, the product between elements is 0, the standard Grassmann algebra. But here I'm identifying one Grassmann algebra using the wedge product, which is, there's nothing wrong with that. But I'm leaving the dot product, while here I'm defining what I want the dot product between any 2 of those null vectors to be.
Okay, but when you define the product from EA and EJ, in the expression 1, I remember you use the scalar product, and here you are using the exterior product.
Yeah, that's the difference, because in one case we have a width basis of orthonormal vectors, null vectors in that case, but in this case they're not orthonormal null vectors. They all have inner product equal to 1/2, or satisfy this property. We're now talking about a geometric product, where I've separately identified the wedge product as being a Grassmann algebra of these null vectors, and the inner product I'm setting all equal to 1/2, and I will identify exactly what geometric algebra or Clifford algebra we're talking about, which is what proves that these relationships are consistent. Now, I was very confused myself. In fact, okay, so the interesting idea is that with this table, this multiplication table, which I'm now identifying for any pair. So in this case, I'm defining A equal to Ci and B equal to Cj. then A times B plus B times A is equal to 1. Okay, and that's where this multiplication table follows from then. But we're
Yes.
only talking about one Grossman algebra now, not two globally dual Grossman algebras. There's a difference there that, and that's why I like to relate it to more into quantum mechanics, justify why I'm calling it quantum duality between Ci and Cj. Any pair of these null vectors, C1 up to Cn plus 1, they're all related in the same way. They all satisfy this basic relationship. And I'm going to tell you exactly what geometric algebra those over the real numbers, for example, that they generate. And then again, once we have that, then any other geometric algebra of any other signature, the matrices can be found by relating it to the spectral basis then. Okay, so let me, okay, so there you have it then. That's a key idea between that's why I'm using now separate symbols instead of A and B for two null vectors of two different Grossman algebras. I'm using a set of null vectors C1 up to Cn plus 1 belonging to a single Grossman algebra, which I call wedge under the wedge product Cn plus 1 over F. Again, I will consider F to be the complex numbers when we talk about the Dirac matrices in the second example that I'll give. Okay, so that's very important. I spent quite a while getting this notice that the property 9 is identical to 7 by choosing A equal to AI and B equal to J for any two pair of these vectors. That's why I call it a local property, because any two of those bivectors are related by this multiplication table. So what I'm claiming really is this is another way of defining matrix multiplication, because when I identify them with matrices, instead of multiplying rows times columns and all that stuff, I'm saying that this is really equivalent to matrix multiplication. But another way of defining matrix multiplication and studying matrices are using this simple multiplication, which is a local definition of the basis vectors, null vectors of the matrix algebra, the corresponding Clifford algebra, C1 up to Cn plus 1. So you can see the distinction then. Okay, but I agreed, I have to show that it's consistent, everything's fine. So okay. The following, okay, I try to explain a little bit. Algebra generated is two conditions is the generated is C plus N plus 1 over F. The two conditions for local compatibility should be compared to the conditions for globally the correlated pair of Grossman algebras given in the previous section, whereas globally correlated Grossman algebras are an equivalent representation of dual vector spaces. A locally self-compatible geometric algebra represents a new concept, which I have dubbed quantum duality in the reference 8. Well, that's the other paper. Itinerant quantum integers, the language of quantum computers, what I'm trying to get people to. By the way, I've only posted that so far on my my ResearchGate site, but I've had considerable interest in it with about 135 different viewers. I have not yet had it posted on ArchivesX, but anyway, and it's not published yet either. Okay, so let me now give the corresponding theorem 2 to contrast with theorem 1 of the previous section. The following theorem shows that locally compatible algebra G plus N plus 1 over F is a specialized width basis. Notice I call this a specialized width basis. Standard dual width basis between is where the inner product of the null vectors is 0, and that's what I call standard width basis. And my specialized width basis, which is I don't believe has been studied before, are I claim now our width basis for the geometric algebra G1n. So remember now, for the standard, for the mother algebras, what people call mother algebras, those are the geometric algebras Gn comma n, or over the complex numbers Gn n plus 1. Now I'm looking at geometric algebras of the form G1n, okay? And okay, so I consider that to be the geometric algebra generated by the null vectors, the n plus 1 null vectors C1, C2, up to Cn plus 1, satisfying those two properties. Well, here they are. That they're linearly independent under the wedge product. So we have one Grossman algebra, and they're locally parallelized compatible or dual, okay, as I called quantum duality there. Okay, so the proof of this theorem is very simple. Okay, locally compatible of the Grossman algebra wedge. Okay, we're talking about one Grossman algebra over F, which, okay, think about it as the real numbers. First of all, that will, and the second of all, the Dirac algebra, where when the matrix is complex, that is a representation of the Dirac algebra, but I'll talk about that. Width basis, specialized width basis for the geometric algebra G1n, where E1 is equal to C1 plus C2, and F1 is equal to C1 minus C2. But notice now I say, I want to find, remember now we have E1, F1 up to Fn. So Fk, now I'm taking between k equal to 2 and n. Okay, because remember we start with E1 defined equal to C1 plus C2 and F1 defined as C1 minus C2. But notice that it doesn't matter what vectors E1 and F1 you choose. It could be Ci and Cj for any pair of these generating vectors of that Grossman algebra identified with the wedge product. So now I'm defining alpha k. That's pretty strange. It took me a long time to properly understand what's going on there. And the thing is that if you try to do, as I say, I'm claiming that matrix multiplication of rows and columns is really, in some sense, equivalent to this definition of matrix multiplication. It's just a different way of looking at matrix multiplication in terms of the corresponding Clifford algebra. It's well known that any Clifford algebra are isomorphic to either to matrices over the real numbers or complex matrices or pairs. You know, there's also special other cases that you have to look at in detail for studying the structure. What did I do here? No. Okay. No. Where am I? How did I do? I lost my screen here. How do I get it back is a question.
Still see the same screen in the share.
Oh, okay. Oh, okay. I can just click that maybe. Okay, here it is. All right, let's see here. Now I'm trying to get it back. How do I get it back?
Perhaps if you might need to stop your share and then share it again.
Oh, okay, let's see. Okay, I got it back, thanks. Okay, I'll try not to do that again.
Okay.
Okay, so that's a simple definition. But you can see that generates the standard basis of this geometric algebra, G1n, generated by one vector which has square plus one and n vectors which have square minus one. Okay, so that's just a basis for that geometric algebra. Instead of using the mother algebras or the complexification of those mother algebras, I'm now looking at matrix algebra in terms of these geometric algebras 1, n, where we can either take this over the scalar field of real numbers, over the scalar field of complex numbers, or in fact any finite field of characteristic not equal to 2. Okay, now I'm saying then let J equal the square root of -1 in order to adapt the matrix representation used in theorem 1 and my definition 8 in terms of the spectral basis for a matrix representation of the geometric algebra G1n. We use the imaginary number J. So now I'm actually considering the complexification to change the signatures of these base geometric algebras, which is of equal importance to the so-called mother algebras, which are the standard representation of a matrix algebra in terms of the dual basis, or what I'm calling dual Grossman algebras, so the Clifford algebra Gn, n of neutral signature, or Gnn plus 1. Okay. So here I'm trying to do that. So I want to define I'm going to try to define now the C1 up to Cn plus 1 in terms of the null vectors. Well, in this particular geometric algebra, G4, 4. Now notice that we know that Clifford algebras have a periodicity of 8. So really by only considering up to C plus of 8, I'm covering all geometric algebras in any matrix algebra which corresponds to it because of this periodicity of the structure of a Clifford algebra or geometric algebra. Okay, so notice what I'm doing now. That's the usual standard basis. I'm looking at, so I'm saying that the Clifford algebra C8 over the complex numbers is isomorphic to the geometric algebra G4, 4. And how I'm going to do that? Well, I'm going to define E1 equal to A1 plus B1 as I did before, F1 equal to A1 minus B1, C1 minus C2. Okay, because they obey exactly the same table as we already pointed out. And then F2, I'm going to define as A2 minus B2. Okay, so that's going to be orthogonal in the usual by using the standard, what I call the spectral basis of dual Grossman algebras. And now notice what I do to F3. I multiply it by J. Well, J is the square root of the usual imaginary number, the square root of -1. So I believe that to really answer properly the question of what is I equal to the square root of -1 represent in quantum mechanics, you not only have to consider just J equal to the usual square root of -1, but you should consider the geometric interpretations as pseudoscalars of the geometric algebra Gn plus 1, which is exactly the case of the Dirac algebra. So it still might be that maybe quantum mechanics needs to have J equal to the usual square root of -1 and not give it the interpretation as a pseudoscalar element in for the Dirac algebra G2, 3. But well, I'm not going to try to. I'm going to show you an example of that, though. Okay. Anyway, this is just okay. So I'm not going to talk too much about that. But remember, I'm using the notation C2 means. Okay, here I define it down here.
Because you have a capital C and lower c.
Yeah, remember when I use the A's, I use the notation AN to be the sum, A1 plus A2 plus A3 plus AN. So I'm using the same notation here. C4
Okay.
means it's just the sum, C1 plus C2 plus C3 plus C4. Oh, yeah, so I'm really, in this case, okay. Anyway, so this is an interesting point. So what I'm trying to do is represent the geometric algebra in terms of matrices now by complex matrices, if you will, by changing the signature of the algebra G1 comma n, just as we changed the signature of the dual Grossman algebras n comma n to get other signatures of geometric algebras. So it's the same idea, but instead of using the usual identification with well, that's this whole question that Dr. Page is addressing of what exactly, how is it proper to identify the geometric algebra GNN? And I've had discussion with Dr. Ojevich too. It goes back many years actually. And well, but okay, I can't really talk too much about it at this point. But okay, the interesting point, another definition of the geometric algebra G plus 4, which is isomorphic or equivalent to the, well, it's equivalent to the algebra G1,3. Okay, well, that algebra you might recognize, that's exactly the Dirac algebra. That means you have 1 gamma 0 squared equal to 1. And then you have gamma 1 squared equal to gamma 2 squared equal to gamma 3 squared equal to -1. Those are the generators of the Dirac algebra, which of course is very important in all of quantum mechanics. But the interesting thing here I'm trying to make, well, I'm using a different notation. Instead of using gamma 1, F, gamma 2, gamma 3, gamma, well, that would, they would call that gamma 0, gamma 1, gamma 2, and gamma 3. The standard notation that people use for the Dirac algebra, but I'm calling it E1, F1, F2, and F3. So it'd be gamma 0, gamma 1, gamma 2, and gamma 3, and comparing it to the Dirac algebra. But notice now I'm defining it in a different way. I'm defining it as a sum C1 plus C2 plus C3 plus C4. Notice that all I'm doing here, I'm taking C1 minus C2. I'm taking 2 minus signs and 2 minus signs, different minus signs to identify. That's the interesting thing. Now I think this is more interesting than this other definition I gave, but I'm not sure that it works for any signature because, you know, somehow we're just changing the sign of the basic element C1 plus C2 plus C3 plus C4. Now, it's not quite right here. I should standardize it because if I take this element C1 plus C2 plus C2, 3 plus C4, and I square that, I actually get 4 things taken 2 at a time, which is 6. So I really should define that as C1 plus C2 plus C3 plus C4 divided by the square root of 6, because I want it to be the standard basis, not, it's a multiple, you know, it's just a scalar multiple by the square root of 6, to divide that by the square root of 6 to get it to have E1 squared equal to 1. But that then relates it back to this other definition. Anyway, some very interesting points that could be discussed in more detail. But maybe I'll go on a little bit so you can see a familiar example, namely the Dirac algebra. Okay, now, how do we usually identify the Dirac algebra as a Clifford algebra or geometric algebra 1,3? Now, I generated, in a number of my past papers, I generated the Dirac algebra by choosing a primitive idempotent in this way. Now, so think about now my E1, E2, E1, F1, F2, F3 as being the standard Dirac vectors in the Minkowski space-time. Gamma 0 is E1, gamma 1, gamma 2, gamma 3 as the F1, F2, and F3. So you see this is interesting as far as that's concerned, because it gives a different way of looking at it, which but again, you have to check the multiplication table that these things, by using that table 1 for multiplication, you can see that, well, up to I have to, like I say, I have to divide this element by the square root of 6 to get it to have magnitude 1. E1 squared has to equal to 1 in the standard basis. But then you get exactly the definition that I gave earlier for those. Okay, so the standard Dirac algebra can be identified by a primitive idempotent, which is the matrix corresponding to 1, 0, 0, 0, you know, all other zeros except in the first row, 4x4 matrix. And that's we can identify it in this way: 1/4, 1 plus gamma 0, that's an idempotent. But notice now what I'm doing here. Normally, the bivector gamma 1, 2 in the Dirac algebra will have square -1. But I need it to be an idempotent, so I have to change. I have to complexify it with I equal to. Now I'm thinking about J as just being the square root of -1. Okay, so that's why people discuss what is the interpretation of the complex number I in quantum mechanics. Well, Hestes has written many papers about that idea as well. I do give some references to Hestes' original work, namely his book Space-Time Algebra, which is what he had just finished writing when I became his graduate student back in 1965. So this has been around a long time now, but this particular way of representing the bases, this was my own idea to relate it as now I'm recognizing what I call a spectral basis is really just another way of looking at, in light of this, what I call dual, quantum mechanical dual. It's just another way of representing the matrix product. Instead of using 2 Grassmann algebras, which are compatible, that corresponds to the usual definition of duality, I represent this unusual local definition because any 2 pair of these all these null vectors have inner product equal to 1/2, which is pretty unusual. And okay, anyway. So this is the primitive idempotent in the algebra. Let me just go on because you can see more detailed references later. Okay, now look at this. Now I'm taking the Dirac bivector 1, 2, and notice I'm just putting gamma 0 in between. So that's gamma 1, gamma 0. Remember, gamma 0 squared is 1. That's that defines a reference frame in relativity. This is Minkowski space-time. Okay, in Minkowski space-time, each unit Dirac vector, which has squared +1, defines a reference frame of an observer. Okay, and this is going back to Hestes' ideas, which you'll talk in any detail I would have to. But anyway, this is now Hestes' definition of the standard Pauli algebra. So I'm representing now the even subalgebra of the Dirac algebra. I'm identifying that with the Pauli algebra. Each observer defines a different, by choosing a gamma 0, that defines a unique inertial system in Minkowski space-time. And the even subalgebra is the algebra of observables, or the Pauli algebra, which is isomorphic to the geometric algebra G3. Okay, so you can see how all these ideas tie together. But what's missing is the idea of quantum duality, which I think is necessary to properly understand. Well, I think it's a natural language for quantum computers, as I emphasized in the previous paper. Okay. So for the idempotents, U plus minus identified by U plus minus 1/4 gamma 0. Notice I'm complexifying. That's why we're using a complex matrix representation of the standard Dirac algebra. And I have these other Okay, we have 4 of these things, 4 idempotents, plus, minus, minus, plus, just changing the sign of these idempotents, which are, this is now a primitive idempotent in the geometric algebra G13. Okay. Okay, and notice now okay, primitive idempotents, U plus, minus, plus, 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 are mutually annihilating since the product of any 2 of them is 0, and they partition unity. Well, because if you sum up the elements on the diagonal, so that's the spectral basis, that's the usual spectral basis for the 2 geometric algebras identified by the A1, A2, B1, B2, and the usual generalization to represent it as a spectral basis idea. Oops, okay. Go back a little bit. Okay, so that's the spectral basis. And that's where I'm using these elements from the previous table to try to get a matrix representation. I haven't really worked completely out the details of this, but you can see what it corresponds to then. A1, A2, B1, B2 then becomes, in the terms of the Dirac algebra, this expression. So I haven't really completely worked out these ideas. What I think is needed to develop this approach more thoroughly is to actually work out a table, a multiplication table for this new definition of matrix multiplication using this local basis based on this multiplication table 1 for matrices. And I think there's a lot of work to be done here. And of course, that's why I'm interested in using that table 1 for multiplying matrices together. I can understand why people have latched on to Cayley's definition of a matrix and matrix multiplication and all that, because you don't have to identify what's a vector or a bivector in your particular representation and all this stuff. But I think it's extremely important, and it needs to be recognized that the so-called, what I'm calling quantum duality, is equally important as the ordinary multiplication of matrices defined in terms of rows and columns of a matrix. Okay, well, I'm trying to identify I don't really do much with it. I'm just trying to identify what these matrices will look like. For example, the matrix of E1, that's more of the standard definition of a matrix of the Dirac algebra that we're looking at, but I don't want to look at it. Okay, well, that's about all I have actually. So the most important example are the Pauli algebras. If you're interested in pursuing this, keep examples as simple as possible. And that one of my papers that have gotten quite a bit of recognition is what I call the hyperbolic number plane. Instead of extending the real numbers by I equal to square root of -1, that's the definition of the usual complex numbers. We extend the real number system with one idempotent, one primitive idempotent, if you will, that has square plus 1, which you say is not equal to plus or minus 1. So it's a new square root of plus 1. That's defined what I call the hyperbolic number plane, and I have a paper. I think I referenced that in my references here. Maybe I didn't. Can't remember really. I should have that paper down here, but I guess I don't. But anyway, it's referenced in many. Oh, you can find it in this book, Matrix Gateway to Geometric Algebras. I'm willing to, I think you all have a copy of the at least the electronic version of that. You'll find a chapter devoted to the hyperbolic number plane, which comes from a paper that was published in the College Mathematics Journal. So it's basically the chapter is a reprint. I think it's the first chapter, or either the first or second chapter of my book. Can't remember. I'll check. Yeah, the hyperbolic numbers is the first chapter of my of my book, Matrix Gateway. So these are the other references. So again, I made sure to reference Hestenes' book, Space-Time Algebra, Gordon Breach, 1966. There's a more recently published edition that you can find on the web, which talks about, again, I think that's a very important idea that Hestenes discovered, or maybe relating the Pauli and the Dirac algebra. The Pauli algebra is the even subalgebra, is identified as the algebra of observables in the Dirac algebra, defined by a reference frame, which is defined by the gamma zero. Each reference frame is defined by gamma zero. And if you look at the even subalgebra generated in that basis, you have the Pauli algebra, the standard Pauli algebra then. So anyway. So again, I will maybe go back to, since you all have a copy of this paper, I'll go back to my page 4, which is what I like to emphasize. I claim that this is an equivalent way of representing any multiplication of any two matrices local by a local definition of what we mean by matrix multiplication. So by this simple multiplication table, I claim you can get the usual matrix representation of any Clifford algebra or any matrix algebra. So again, I think one should think about a matrix as a coordinate matrix of a Clifford algebra or a geometric algebra. But of course, what makes that a little bit confusing is because there are many isomorphisms between Clifford algebras. But what's important is the anti-commutative property, which is, of course, relegated to fermions. Fermions are anti-commutative in physics. And you have bosons, which correspond to the symmetric relationships. But this idea of this multiplication, any two null vectors defines a Pauli algebra and a Dirac algebra corresponding to. So that's why I'm trying to identify up and down quantum states with pairs of these null vectors. Well, maybe complex null vectors are more appropriate. Or, like I say, if you look at the algebra, Hestenes has also written many papers. To avoid matrices, you don't really need complex matrices. You can define it up. Well, anyway, there are many different ways of looking at this stuff. And I hope that this new idea of Hermitian, not Hermitian, but well, actually that's closely related. Remember, Hermitian matrix, again, is a definition of what of an inertial system, or that's right, or a reference frame is defined by a Hermitian matrix.
Professor Garret,
Yes.
I have a question there. Is there any special I don't know, like idea behind name this quantumly dual or quantum dual? Is there any relation between this representation and if you can derive some quantum mechanical properties or?
Well, actually, I'm communication with Professor Kaufman, who's actually they'll be publishing a book of our proceedings of the conference that we had in honor of a memorial conference we had in memorial of Zbigniew Ojevich, the late Zbigniew Ojevich, where he talks about, I got the name itinerant from his name. I referenced his paper in the references. Maybe I'll go down to his references. because that's where my ideas coalesced around. One of the things he does in his paper, let's see, where is the Kaufman? That's Kaufman here, I guess. I don't have Kaufman's paper. Okay, so you have to look at my paper, Itinerant Quantum Integers, okay? I don't have that. I guess I have it. Let me just, I have that paper here, but I don't have it. I think you have that paper. I sent that to you last time. But the reference that I want to point out is in that paper, it's the reference itinerant. He calls them iterants, Majorana's fermions and Majorana-Dirac equation. And then he has another reference. Oh, well, another paper was, well, I have three references in that paper. References 9, 10, and 11. Okay, construction for Clifford algebras. That's in an Archive X paper of his with another author. And well, anyway, but one thing he does in these papers is he shows how to, by introducing the structure of the symmetric group of well, you know, the symmetric group is just permutations and combinations, permuting n plus 1 numbers, or say n numbers. You know, you have pairs. The pairs generate all. The permutation group is generated by pairs of numbers 1, 2, 1, 3, and so on. You generate all the. And what Lunesto does is in this paper, most distinctly, I think in the first reference, the itinerants, that's where the name of my paper came from. He represents the symmetric group in any Clifford algebra in terms of this new operation that he defines to represent the symmetric group. Well, what I show in my paper, itinerant, what I call it, quantum integers, that you can do this all in the geometric algebras G1n without introducing additional structure. So it's a different way, but he clearly relates many ideas in quantum mechanics using this particular structure. So I believe, and I'm trying to get him to help me out on some of the, well, to become interested in these ideas as well, because it's obviously very closely related to quantum mechanics. And I referenced my own work on the Pauli algebra and the Dirac algebra to try to highlight, well, for example, Hermitian matrices and the rest of the structure of how to construct what I think would be the ideal language for quantum mechanics out of what I'm calling now in this earlier paper, itinerant quantum integers.
So
Okay.
it could be like understood like a parallel definition, not using the standard Hilbert space definition, right? It's
Well,
like
that's right.
another.
That's one of the major emphases of Hesni's work, to use geometric algebra instead of always representing everything in terms of matrices and the bra and the ket and all the matrix. You know, quantum mechanics of computers, the language of quantum computers right now is basically matrix algebra and the tensor product of matrices and all that. But you don't really need, I don't believe you really need to do that in a much more direct way. Representing the ideas of quantum mechanics is using this alternative, what I'm calling now quantum duality.
Yes, and also one of the main problems of using even Dirac representation for quantum processes, at least in quantum computing, is that it's not scalable to a greater number of qubits. So it gets really complicated to understand what is behind a certain process or computation. I think your work, it could be really good to read, and for myself at least, because the topic that I told you at the beginning of the seminar, it's also another way to represent these quantum mechanical properties without the necessity to translate it in the Hilbert space, but it's like a kind of different way of seeing things. So I will send you some references too, Professor Garrett, so you can like at least start read it and maybe complement some ideas, and maybe we can discuss which are like the similarities between your theory and this CX calculus theory too.
Well, that sounds very good. In fact, maybe you could present something at a seminar. We can arrange. That of course is up to the organizers, Dr. Cruz and Dr. Page.
Yes,
Yeah, I
certainly,
would love to.
Yeah, I think that would be an excellent possibility. Just let us know at any time when you might want to do something like that.
Yeah, I'm still like researching the topic, because there's a lot of things that I don't understand very well. I think possibly because of my background is not that strong in mathematics, neither physics.
Well,
But
don't
yeah,
let that be limiting. There's no reason to hesitate. I think because this is a research seminar, and that's the whole point of a meeting like this, is sort of to stimulate further research and look at preliminary results.
Yeah, I like to say in that itinerant paper, I have a number of other references which are highly pertinent. In fact, Dr. Havel has done very interesting work as well, relating some of these ideas. And I think that the quantum mechanics, yes, I think I referenced that paper, Dr. Havel's paper with Chris Dorn. You might want to look at that paper as well. So I think they were trying to do exactly the same thing, use Clifford algebra instead of always referring back to tensor product of matrices and all that. Well, I think that this idea of quantum duality does give you an alternative way of looking, a local way of, like I say, any two pairs of these null vectors define a Dirac algebra and a Pauli algebra over the complex numbers. So I think it's a much more direct way of representing these ideas. But again, the details are hard to put together.
yes.
Okay. I thank you very much for the presentation today, Dr. Sobczyk. Where do we go from here, I guess? Shall we plan in 3 weeks' time to switch our subjects back to category theory or graph theory? Is that
Yes,
possible?
I can prepare something for that time. And I think that if Brian like to present something, we can make one slot for his presentation. Then,
Yes.
Mhm.
Okay.
Yes, I can prepare something after Professor Cruz, and I can at least present like the general ideas and how it is studied in the state of the art right now, how they are using it to deal with some quantum computation processes. So And if there is questions or maybe some topics that are kind of living in the air a bit, I can research it further to next meeting. So
Okay.
Well, it's very nice to see a young face interested. So we're very happy to have you.
By
Thank
all
you.
means.
thank you very much.
Okay, well, we look forward to seeing you all again and perhaps some additional participants in 3 weeks' time.
Okay,
And, with
Perfect.
that, say
Well, thank you very
bye for
much.
now.
I enjoyed it.
thank
Thank
you
you
for
all.